We all know that nothing in the universe can travel faster than light. This cosmic speed limit, set at about 300,000 kilometers per second, is insurmountable for anything with mass. But what would happen if we approached this extraordinary speed? How would our perception of space and time change? Traveling at speeds close to the speed of light, we would enter a realm dominated by relativistic effects, phenomena that would transform the reality around us in ways hard to imagine. In this video, we will explore how space-time itself deforms during such a journey. We will discover why everything would appear altered and how our perception would completely differ from that of a stationary observer. What we would see would not only be a fascinating spectacle but also a practical illustration of how relativistic physics describes the universe. Ready to embark on a journey to the edges of speed? Let's talk about the speed of light, an insurmountable limit and one of the most fundamental physical constants in the universe. This speed, precisely 299,792.458 kilometers per second, represents a cornerstone of our understanding of space and time. But the question arises, can we travel at the speed of light? And if we can't, why not? The speed of light, an unbreakable limit. According to Einstein's theory of relativity, it is not possible for a body with mass to reach the speed of light. The reason for this impossibility is not, as many believe, that the mass of an object becomes infinite. Let's clarify. If we were on a spaceship and weighed 60 kilograms, even traveling at speeds close to the speed of light, our mass wouldn't change from our point of view. Inside the spaceship, would still have my same 60 kilograms mass, regardless of the speed at which I'm traveling. The misunderstanding comes from the use of the gamma factor, also known as the Lorentz factor. This parameter increases as we approach the speed of light, tending to infinity. By multiplying gamma by our mass, we get the so-called relativistic mass, which indeed tends to infinity. But our rest mass, the real mass, remains unchanged. However, to reach the speed of light, infinite energy would be required. This is the true obstacle. We cannot accelerate to that speed because there is no source of infinite energy. Photons, which are massless, can travel at the speed of light, but for all objects with mass, this speed remains out of reach. What would happen if we traveled near the speed of light? Even though we cannot reach exactly the speed of light, we can theoretically approach it. But what would happen if we traveled at 90% or 95% of the speed of light? This is where special relativity comes into play with full force, and the reality around us would begin to transform in spectacular ways. The relativistic effects that manifest at these speeds alter not only space but also time and light itself. To help us visualize these phenomena, MIT developed a game called A Slower Speed of Light, in collaboration with physicist Gerd Kortemeyer. In this game, it's not us accelerating, but the value of the speed of light that is gradually reduced, allowing us to observe in real time the visual effects predicted by special relativity. At speeds close to the speed of light, we would begin to see the past, while space would distort before our eyes. Doppler effect. Light changes color. One phenomenon that occurs at relativistic speeds is the Doppler effect. Many of us are familiar with the Doppler effect in relation to sound. When an ambulance approaches with its siren on, the pitch seems to rise, while when it moves away, the pitch drops. This happens because sound waves are compressed in the direction of motion and stretched in the opposite direction. The same principle applies to light, which is also a wave but an electromagnetic one. If we move towards a light source, its light compresses, shifting towards the blue end of the electromagnetic spectrum. If we move away, the light stretches, shifting towards red. But it's not just the visible spectrum involved. Our eyes perceive only a small portion of the electromagnetic spectrum, but with the Doppler effect, we might begin to see infrared or ultraviolet light, normally invisible. Headlight effect. Light becomes more intense. Another curious phenomenon is the so-called headlight effect. When we move towards a light source, the light tends to concentrate in the direction of our motion. This means that we would see objects in front of us much brighter than they would be under normal conditions. Conversely, objects behind us would appear dimmer, as fewer photons would reach our eyes. Length contraction. Space compresses. An even more extraordinary effect is length contraction. According to special relativity, an external observer would see a moving object shrink in the direction of its motion. For those traveling at relativistic speeds, space itself would seem to contract. In other words, the space ahead of us would compress, giving the illusion that objects are receding, when in fact the opposite is true. This phenomenon is called length contraction and contributes to the visual distortion we would experience at such high speeds. Time dilation. Traveling into the future. Traveling close to the speed of light, we would also experience an effect known as time dilation. For those traveling, time would pass more slowly compared to a stationary observer. If we were on a spaceship traveling toward a distant star, we would see the inhabitants of Earth moving more and more slowly, as if they were in slow motion. Not only that, due to the time it takes for light to reach us, we would also see them as they were in the past, younger than they actually are. As we moved farther from Earth, the light coming from our planet would shift more and more toward red, until it completely disappeared from the visible spectrum. As a result, we wouldn't only see time slowed down, but eventually, Earth itself would seem to vanish into the darkness of space. Lorentz transformations. Space deforms. Finally, at speeds close to the speed of light, objects around us would appear curved and distorted due to Lorentz transformations. This happens because, since the speed of light is a universal constant, space and time must adjust accordingly. The distances in time measured by someone traveling at relativistic speeds will differ from those perceived by a stationary observer. Distant objects would appear rotated and distorted, and the farther an object is, the more we would see it as it was in the past. A relative universe. The theory of relativity teaches us that our perception of the universe depends on our state of motion. An event can be seen differently by moving observers compared to stationary ones, and none of them are wrong. Relativity shows us that the universe does not have an absolute truth. Everything is relative to the observer's point of view. We've explored the incredible effects relativity can have on our way of seeing and perceiving space and time. Even though we cannot travel at the speed of light, we can theoretically approach it and experience a universe profoundly different from the one we are accustomed to. A universe where time and space merge, and reality itself becomes relative. Thank you for watching, and we'll see you in the next video.